This talk is about SMCP3, a new family of algorithms for solving sequential Bayesian inference problems. Let's start with an example. Consider a probabilistic model under which an object moves according to a random walk on the plane, creating trajectories that look like this. And say that under our model, at every moment, we also receive a noisy measurement of the position of the object. Here, the red circles are the noisy measurements, and the smaller red circles are measurements from past time steps. The goal of inference in this case is to observe a sequence of noisy measurements and to be able to infer what latent trajectory probably underlies those measurements. You try it. Say you see this sequence of noisy observations. Do you have some sense what the underlying trajectory looks like? Sequential Monte Carlo, or SMC, is a type of algorithm which can solve this problem. Here I'm showing the set of hypothesized latent trajectories Sequential Monte Carlo thinks underlies this data. But there are also many Sequential Monte Carlo algorithms which perform poorly at this task. You'll notice that here, on many steps, the latent hypotheses lag behind where the observations suggest the object is. The main issue with this algorithm is that at every time step, the process that Sequential Monte Carlo is using to update its beliefs in light of new data is not intelligent enough, and this leads to the latent hypotheses getting left behind by the data. SMCP3 makes it possible to use a wide new range of intelligent belief updating strategies in Sequential Monte Carlo, making it possible to solve this inference problem and many others. SMCP3 also makes SMC easier to implement, since the complex calculations underlying its implementation can be automated by a probabilistic programming system. Now, later I'll return and show quantitative results for this experiment, and I'll also highlight other examples in which SMCP3 is used to improve inference for tracking 3D objects from video data, and for clustering datasets being streamed in online. But first, I want to explain what caused that SMC algorithm I just showed to fail, to motivate the need for SMCP3. Then I'll explain our contribution and how SMCP3 can fix that inference problem, and show our experiments with SMCP3. I'll conclude with some of the more technical details of the SMCP3 algorithm. So, to understand how this failure occurred, we need to walk through how Sequential Monte Carlo works. At the first step of Sequential Monte Carlo, we get an observation, and we initialize a collection of particles, a collection of latent positions, hypothesized to be where the object is underlying this data. Then, at every subsequent time step, we get a new observation, and we extend or update each particle and change the particle's weight. We get a new observation, then we extend each particle. Here, each particle is a latent trajectory, which we extend to have a position for the next time step, and we change each particle's weight. Here you can see how we're changing the colors of the particles. The weights characterize how promising each particle seems relative to the others. And this process continues, with us getting new data, extending the particles, and changing their weights in such a way that we characterize how promising each particle currently seems relative to the others. Now, we could extend this algorithm in many ways, for example, adding a technique called resampling, but these aren't too important to get into here. What is important to discuss here is that one of the biggest levers we have for controlling the performance of a Sequential Monte Carlo algorithm is what strategy is used to update the particles at each time step. In this algorithm, I'm calling it the particle updater. To make this concrete, let me show you an example of one of the simplest particle updating strategies we could use, the bootstrap particle update. At the third time step of inference, the particle updater will receive as input this black trajectory over 3 steps, which might underlie the first 3 noisy observations we got. And then at time 4, the update will receive a new noisy observation, and its goal is to update this trajectory in light of this new data. The bootstrap update just proposes a new position for the object from the random walk model, and outputs the extended trajectory. Now, remember that the particle updater doesn't just output a new trajectory, it also has to output a way to update the particle weight. And it turns out that the expression we should use for the bootstrap update looks like this. Now, if you run this algorithm, you run into the issue I showed earlier, where the latent states hypothesized by the algorithm lag behind the data. And this isn't too surprising, because the strategy that this is using to update the trajectory takes into account no information from the observation. It just extends the particle from the random walk model. However, in the SMCP3 algorithm I'll come to later, we use a smarter updating strategy, which does take into account what the data is telling us, and thereby can track the object well. So, if an issue like this can arise, in what sense is Sequential Monte Carlo actually a valid Bayesian inference algorithm? Well, it is a Bayesian inference algorithm in the sense that it characterizes the posterior distribution over latent trajectories given the data, under the probabilistic model, which is a random walk where we get noisy observations. Now, SMC is always guaranteed to converge and characterize this posterior in the limit of an infinite number of particles. In particular, one way that it does this is if you run Sequential Monte Carlo and then pick a random particle with probability proportional to the particle weight, it turns out in the infinite particle limit, that will be a fair sample from this posterior. Now, at first glance, this might seem surprising, given that the distribution we actually generate the particles from is this particle updater distribution, which may be totally different from the posterior that we care about. And the way that sequential Monte Carlo gets around this is that the particle weights exactly characterize the difference between the particle updating distribution, which we used to actually generate the particles, and the posterior distribution we're trying to run inference over. The formal condition, which guarantees that a particle weight perfectly accounts for this error, is called proper weighting. And being able to compute proper weights is crucial to run sequential Monte Carlo. If we can't compute such weights, then we could just generate particles which have nothing to do with the inference problem we want to solve, and we wouldn't have any way to correct for that. But when we do know how to compute proper weights, and we have a good particle updating strategy, sequential Monte Carlo can work really well in practice, even with just tens of particles, like this frame I'm showing here. This brings me to our contribution. SMCP3 makes it possible to use a much wider range of smart strategies for updating particles in light of new data in SMC. It does this by explaining how to compute valid, proper particle weights for a huge new family of particle updating strategies. Furthermore, SMCP3 can also automate the implementation of SMC and the computation of proper weights for any of these particle updating strategies, when it's given the target probabilistic model and the particle update strategy written as probabilistic programs. Because of the broad range of particle update strategies it supports, SMCP3 encompasses and generalizes many types of SMC algorithms for the literature, and thus can be used as a tool to automate the implementation of any of these algorithms, as well as many new algorithms that other SMC formalisms could not support. Let me give you an example of the type of smart particle update SMCP3 makes it possible to use. Recall this situation where we want an algorithm to update this latent trajectory in light of new data. As before, we'll begin by drawing a sample from the random walk dynamics under the model. But in the SMCP3 particle update we're going to develop here, we'll then take a second step, which first moves along the gradient of the posterior distribution, and then applies a small perturbation, and uses this position as the hypothesized object position in the updated particle. By taking this gradient step, this particle update takes into account information from the observation, and thus is a lot smarter about how it is proposing the new value of the particle. Now, we can have SMCP3 automatically run the algorithm, and run SMC with this update, and sure enough, it does a very good job of tracking the object. Now I want to go a little bit deeper into our experiments that illustrate the value of being able to write new types of smart particle updating strategies. The first set of experiments I want to highlight is our experiments taking quantitative results in the type of model we've been looking at, and also in higher dimensional variants of the model. We've compared both the bootstrap updating strategy that I showed to our SMCP3 algorithm, and we also compared this to a smart resample move algorithm that takes metropolis-adjusted Langevin ascent steps for its rejuvenation move. We're measuring inference performance using one of the quantities that sequential Monte Carlo is often used to estimate, the log marginal likelihood of the data. And as we elaborate on in the paper, it turns out that because of Jensen's inequality, estimates from SMC of this quantity will be underestimates of the real value. So higher values indicate better inference performance. We also experimented with a range of computational budgets in which we could use different particle counts and found that across the board, SMCP3 produced more accurate inferences. Now, this is a toy model that I just showed with a random walk prior, but I want to highlight that this SMCP3 algorithm we developed is actually applicable to any online state estimation problem in a dynamic model with a differentiable likelihood. We also developed a variant of this algorithm, which can work in non-differentiable models, and we ran some preliminary experiments using that variant to track 3D objects from RGB depth video. The probabilistic model we used for this posited a simple model of 3D object motion and a likelihood over RGB depth data based on a non-differentiable renderer. Our experiments suggest that SMCP3 makes it possible to track objects a lot more accurately than some simple SMC baselines, and one research direction we're really excited about is scaling up this application and doing more detailed quantitative comparisons. Let me give you a quick sense of how our SMCP3 algorithm for that works. We use a very similar particle updating strategy to before, but of course we have to get rid of the gradient-based step because our model is non-differentiable. Instead, we replace the gradient ascent step with a coarse enumeration step, where we enumerate a coarse grid of possible object positions, and we sample one of the positions with probability proportional to its likelihood under the model. And then we use that position sampled from the grid as the proposed object position. SMCP3 can be used for inference in any sequence of probabilistic models, not just models where the latent spaces are trajectories. To demonstrate this, we also wrote a new SMCP3 algorithm for online data clustering. This visual shows a bunch of clustered data points, Each data point is a real value, indicated by the y-axis, and the data points are streamed in over time. The time at which each data point was observed is indicated by the x-axis. One issue that even good SMC baselines from existing algorithm families suffer from is that they can get tricked by local minima. In this example, you'll notice that the cluster of pink circles and green squares are quite close together, and when you've just observed one or maybe even two of the green squares, you might think that the green squares are just outliers from the pink circle cluster. However, baseline inference algorithms can actually get tricked by this in perpetuity and never be able to realize, even when we've received many data points, that it actually makes more sense to posit that there is a separate cluster of green squares from the pink circles. SMCP3 is able to recover from this failure mode by using a smart particle updating strategy, which at every time step considers if it should split one of its hypothesized existing clusters into two clusters or merge two hypothesized clusters into one cluster. We again took quantitative measurements of inference quality using the log marginal data likelihood estimates, both on toy datasets like this and on a corpus of real data from the US Medicare system, where the data points weren't real values, but were strings that were to be clustered together. So, how does SMCP3 enable the use of such a wide range of particle updating strategies? We use as our starting point one of the most general ways from the SMC literature to update a particle, the forward-backward SMC update. This update allows you to use a completely custom strategy to propose an updated particle, given the old particle, as long as you also provide a backward proposal distribution, which given the updated particle, proposes what the old particle may have been. It turns out that having a backward proposal makes it possible to compute particle weights. Now, in the classic forward-backward update, the forward and backward proposals have to make it tractable to compute the probability density of an updated particle given the previous one, and vice versa. But in SMCP3, we generalize this by making it so that the proposals can be general probabilistic programs. These programs need not admit tractable densities over the particles they output, and indeed, they may sample auxiliary random variables and apply deterministic transformations. In this way, SMCP3 removes strict restrictions on what types of proposals can be used to update particles. SMCP3 also builds on support for automated SMC from past probabilistic programming languages, many of which allowed users to use probabilistic program syntax to write proposal densities, while SMCP3 makes it possible for users to use general probabilistic programs as proposal distributions, as long as the proposals they write have the correct input-output interface. Now, in the paper, we walk through how to generalize from classic forward-backward SMC to SMCP3, and exactly what the particle updates look like. But in this talk, I'm just going to flash through what it looks like in our example. So the idea is that we can write this proposal process we described earlier as a probabilistic program. The second thing that we need to do is write a backwards proposal, which takes as input an updated particle and approximately inverts the forward proposal, proposing what particle may have been input to the forward proposal before the update, and what set of random choices the forward proposal may have made to cause it to output this as the updated particle. We can write such a proposal using a probabilistic program, and once we have these two proposals, and also a probabilistic program describing the random walk model we've been using, a probabilistic programming system can automatically run SMCP3. How can SMCP3 be automated? Well, to update a particle is easy. We just plug it into the forward proposal and see what updated particle it outputs. So the real question is how we can compute particle weights for these updates. And in the paper, we prove that if you update particle weights via a particular expression, you get a properly weighted SMC algorithm with all the normal convergence guarantees you'd expect from SMC. And we also prove what the optimal backward proposal is. It is one which inverts the forward proposal in a certain precise technical sense. Now, how do we automate this expression, the computation of this weight? The short version is that most of these terms can be automatically computed using standard probabilistic programming operations, and the other term is a change of measures term, which boils down to the Jacobian of a specific function, which can be computed using a new algorithm we've developed for sparsity-aware forward-mode automatic differentiation. We work this all out in detail in the paper, but as a user of SMCP3, you really don't need to worry about how we compute particle weights. What users need to focus on is coming up with good strategies for updating particles and good strategies for approximately inverting these updates. We believe that SMCP3 is a step toward enabling practitioners to focus on that and not on implementation details or on reshaping their intuitions about what particle updates they want to use into a form accommodated by more restricted SMC algorithm families. We're really excited by the range of inference algorithms we've already been able to implement using SMCP3, and we're even more excited to see what new types of problems practitioners will be able to tackle with sequential Monte Carlo using probabilistic program proposals. If you're interested, please check out our open source repository for automated SMCP3, and please engage with us in the comments of this video, over email, and at AISTATS.